All right, so we are going to do Lagrange Mechanics Part 4. Part 4. Now, if you have not done this with me in the past, this is my notebook. I have all of my notes. We are following Taylor, Classical Mechanics, and I put all of my notes on Discord, so you're welcome to hop in the Discord, !Discord if you're watching me on Twitch. If you are watching me on YouTube, you can find the Discord link in the description below. Now, so all of my notes are on Discord. All right, so let's start. We're on Lagrange Mechanics Part 4, but let's start like we always start, and always feel free to chime in. Of course, !Speak is on for everybody, so if you have a question or want my attention, !Speak. If it gets abused, I will turn it off for everyone and only on for subs, but I'm assuming it won't be because you guys are all great. Let's do Lagrange Mechanics Part 4. And, Lagrange. I forgot the R. I was like, something in here does not look right. And unfortunately, it's not Lagrange Mechanics right
Everyone
now.
can use. Speak, so don't abuse it ever.
Part 4. Now, I can't use my entire board, but I think that I can probably get to, like, here safely. So maybe we'll try to use like that. And if you guys can't see anything, speak up and be like, I can't see. And then I can stop and make it so. So last time we talked about 3 equivalent statements. Again, I'm not going to write everything down on the board. The notes are available on Discord, especially like they're kind of wordy this time, because I feel like there's a lot to just talk about. We also have a couple demonstrations we're going to talk about. So we'll show those. We'll get those out and rolling in a second. So last time we talked about the 3 equivalent statements. Okay, that's what we started with last time. There is 3 equivalent statements we could talk about with a particle and about the particle's path. The first statement is a particle's path is determined by Newton's second law. We figured out that you could figure out the acceleration, F equals ma. There's all sorts of stuff you can do. You can change that into energies and do different things with that. Then the next thing we talked about is a particle's path is determined by the Euler-Lagrange equations. That is our famous, so we have the first one, I can write this out, the first one is F equals ma, Newton's second law. The second one is a particle's path is determined by the Euler-Lagrange equations. And let me write those down. The partial of the Lagrangian with respect to the parameter, the variable, is equal to, not the parameter, the variable, d dt. And we've taken a couple weeks to prove these, so we won't go into it again. If you are watching on YouTube, the first 3 parts, you can find them. If you're not watching, if you're watching on Twitch right now, you can type !YT to get to my YouTube channel where you can get caught up if you would like to. And then, so this is the second one. The third one is a particle's path is determined by minimizing the action, where we have the action is given by S is equal to the integral from t1 to t2 of the Lagrangian with the variables that we have talked about, q dot, and t dt. Okay? This is the Newton-Witten equation. Look, you can't just put Witten's name on it. Actually, you probably could. Okay, so what do we do with all these? Well, we found that the Euler-Lagrange equations last time could be extended to many particles in the unconstrained. Today we'll talk about many particles constrained. But we talked about many particles unconstrained. We also evaluated a constrained system, the simple pendulum. We found that the Euler-Lagrange equations produce the equations of torque. So for a simple pendulum, we found that we could actually describe it with our equation of torque, where we have the inertia and the angular acceleration. So let's get out a little bit of something. So if you are looking at the notes, the next thing says about free will, but we won't do it yet. Not free will. Wow. Chaos. Not free will. Please. Please. It's covering interesting topic today, and if this is evidence that the universe is determined from the strength of everything. All right. So I managed to whip up this contraption today. This is one of the harder builds I've had to do. So, simple pendulum, and we figured out that the equations of motion can just be determined by the torque. Torque being best thought of, at this level at least, as a like an angular force. It's a good way to think about it. Least action sounds like Tyrion, am I right? Hey-oh. All right. So let's get into the stuff for today. Now we're going to talk about systems in general, and now we're going to consider arbitrary systems of n particles. Okay. So let's get some. So we're going to leave this here, but we'll have to come back to it in just a second because we're going to add to it. Boop. I wish I had a lab assistant. Dennis was here for lunch today, and he helped me with it. And then I realized he's not here now, so I don't. Maybe I haven't thought this through well enough. That's okay. We'll figure it out. Okay, so let's get on to some of the new equipments. Now we're considering constrained systems in general. Okay, so we want to start. So I'm going to erase all this stuff. So we proved that these things were all equal, and then what we could do with them, and just generalizing some of the Lagrangian. Okay. Lagrangian for many particles, are they popping in and out of existence? Nope. I don't think so. Where did I put my chalk? Got it. Okay. So we are going to let's first label a couple things. We can talk about the position of the particles given some distance r, some displacement vector, if you wish. I'm not going to be carrying vectors through this entire time. But you can pretty much generalize which vectors are where. So the r is the displacement vector, and then we have our generalized coordinates. So we have our generalized coordinates that are going to be going from q1 ... to q. Where's my Taylor? It'd be a bummer if I already made a mistake. You guys, I'm a little bit rusty. Okay, go lightly on me today. I did make a mistake so early on. So it's supposed to be a lowercase n in the notes attached to the Q. I'm surprised I caught this that fast. Okay, now it's fixed. So in the notes, it's supposed to be to little n. Okay, so then we can talk about, let's see, we can talk about the following two expressions. We can talk about r, the displacement vector, as a function of the generalized coordinates, q1, q1 to qn. And in this, we can talk about how alpha is going to run, not defined, alpha is going to run from 1 to n. And then we want to also be able to rewrite the coordinates, qi is equal to qi as functions of these displacement vectors. Now this is going to be, we're generalizing this up to n's, but we're going to be using some pretty concrete examples. One of which maybe you've guessed by now by the fact that I pulled the pendulum out. So again, to illustrate this relationship, we want to consider the simple pendulum, because that's what we've seen, that's what we've done. And we can rewrite the equation for the displacement defined in some xy coordinates, or we were able to reduce it, and this is a lot of what we did last time, we were able to reduce it to having one parameter. L sine of phi was the x, and L cosine of phi was the y, and this means that we had one parameter, or one generalized coordinate, which was phi, right? L was a length, so that's not a generalized coordinate, that's just a measurement, a constant, if you will, okay? And with that, we were able to express r, and that's kind of one of the general, or I called it the important requirement. Actually, Taylor called it an important requirement. Is we want to express r in as fewest coordinates as possible. So having just one generalized coordinate, that's the fewest coordinate we could express r in, and that's why it was helpful to have that, right? But now we can consider something different, right? Let's consider, I would call a constraint. Okay. I don't know, is that what Taylor called it? Anyways, I think constraints kind of have like the, well, never, anyways, let's keep going. Okay, so now we can consider something different. So let's consider a double pendulum. Now, double pendulums have a couple of cool, interesting properties. I think I can just put all my books on it to hold it in place. Let's get rid of this. So let's put the books on this to kind of hold it in place. We'll turn this. And then we'll see some cool things here. We'll take a look at the motion of this first, the motion, and then we'll look at a quick little animation that I found on Twitter that's relevant. Okay, so now we have a double pendulum. Okay, and there's something interesting that happens with the double pendulum. Thanks, BMP. I crafted them up today. Anyways, before I keep going. But watch what happens. Now we have a couple different parameters, right? Like, for instance, we can take this and put it out like this, and we have a couple different angles to consider, right? We have this angle right here that makes with this horizontal, and we also have this angle right here that makes with this golf ball. Pull it a little bit closer, maybe. There we go. So now let's see what happens when I release. Now we have some weird motion between the two, right? Like, there's definitely something odd here. And it turns out that this system's actually chaotic, which means that you're going to have trouble.
A little bit weird.
Thank you for the follow, Dricksport. Yeah, so this is actually chaotic motion, and we'll talk about chaos in a second. I just have a couple notes on it. But you can just see here that when you release these things at different parameters, we have some different odd stuff happening, right? Like, there's definitely not an easy way to describe the motion of this. And let me show you a little bit of a stronger example of this. Hopefully, if this plays. I don't know if this will play or not. This is Daniel Litt, very brilliant mathematics professor. I don't remember where he is. Somewhere south, I think. But he posts great stuff on Twitter. But this is one of them. This is a series of pendulums. And notice what happens very quickly once you get into it is, there it is. It gets very chaotic. Now, if there wasn't chaotic motion, you would expect them all to just sort of follow the same path. But instead, what ends up happening is after you get to a certain time elapsed in, the paths all change dramatically. And this is something that we can talk about with, but yeah, so this is kind of what we're talking about here, where we have this, after a little while, it becomes chaotic. Yeah, exactly, Arc. So, let's talk a little bit. I just have a couple things about chaos, and they're generally relative, they're related, wow, to this topic, because, we'll eventually see that if, I don't know if we'll do the double pendulum. Maybe we'll do the double pendulum at the end, because there's a nice calculation in Taylor about it. But if you have a nonlinear motion, most systems with nonlinear motion. Now, we can talk about the simple pendulum in linear motion, right? It was just, but we can't talk really about the, actually, I don't know if we could talk about it in linear motion. We'll have to. Actually, I have to be more careful about the things I say, but it doesn't matter because we can model a simple pendulum pretty easily. It's this system will not be linear at all, and it will therefore be, and it's definitely one of the chaotic systems. So another symptom of chaos is it has more degrees of freedom than there are conservation laws. That's something you'll learn in quantum mechanics, kind of, is if you have more degrees of freedom than conservation laws, then you will also exhibit some chaos. But there is no real definitive mathematical expression to describe chaos. So even though we can say, like, most systems whose equation of motions are nonlinear exhibit chaos, we can say that most systems with more degrees of freedom than there are conservation laws, they usually exhibit chaos. But there's no real definitive mathematical expression that will actually express something is chaotic or not. So those are our notes on chaos. And now, are we into... Okay, so yeah, there we go. We're not quite into the degrees of freedom yet, but I'll talk about degrees of freedom more thoroughly. So if you're wondering what a degree of freedom is and how it's relevant to having not as many or more degrees of freedom than conservation laws, then we'll talk about that in just a second too. So now we can talk about the double pendulum. We saw an example of it. We saw an example of a bunch of pendulums. And how do we describe those? Well, we can talk about the displacement of R1. Let's draw a little picture. So we have everything written down. So we can talk about this would be like phi 1, this would be like phi 2, where those don't have to be the same thing. We could even talk about L1 and L2, the length of one string or rod, whatever you're doing, versus the length of the other string. And then we can say that R1 looks like it has coordinates L1 sine of phi 1 and L1 sine of phi 1. Now cosine, excuse me. Now we can see that this has a very similar situation to what the motion of a simple pendulum is. Okay, so, but this is not enough. We can talk about the second bob, as in ball at the end of the rope. And this also has another form, and it looks like this. This one's a little bit more in-depth. Sine of phi 1, and then, plus L2 sine of phi 2. And these are just this is not the actual, not the actual displacement function, but this is just the variables of that function. L1 cosine phi 1 plus L2 cosine phi 2. And this is about as generalized as you get it, but you see that R2 is going to end up having, it's going to be a function of phi 1 and phi 2, right? Whereas this is still just a function of phi 1. So now we have this system where we have, we can no longer rely just on one parameter or one generalized coordinate. Now we need at least two generalized coordinates. Oops, I forgot to close that. There we go. So now we're going to have at least two generalized coordinates. But even these, we can talk about examples that do not depend on time, right? Well, why? Well, because you can talk about time and write it as of time, but it's not going to be the smallest amount of generalized coordinates. No, instead you'll have, you'll still have to talk about time. And nevertheless, we can talk about something that does depend more dramatically on time. So how about this? Consider you have like a train car, right? This is another way to take a one-coordinate system. So say we have a pendulum, and there's some velocity or acceleration, with the the train car. What did I draw? Anyways, I drew the picture from Taylor, and it looks weird to me. So we can still see the simple pendulum inside the real car. And Bryce, feel free to hit exclamation mark ask in your question, and I will handle it probably when I'm done with this, which this won't last too terribly longer. If you don't mind waiting, just hit exclamation mark ask in your question, and then it will go to a separate thing, so I don't have to worry about chat missing it. So we have a train car, and it's accelerating a certain direction, and our bob from the simple pendulum is going to be displaced. And we can sort of talk about how much it's changing as a function of time, right? Because of the acceleration, right? As it accelerates faster and faster, it's going to be getting more and more out like this, to the point where like you're going as fast as possible, and it's like flying way up. And you could talk about that because we can talk about the position using that function that we talked about earlier from Nicodemus's question, right? Where we had this relationship between the and now we are in x direction because we're talking about the acceleration this way, right? And kinematics comes right back, full circle, just like we talked about with Nicodemus's question. And this becomes a function of x and y, but also the parameters become L sine phi plus, now we're in the x direction, so we have the 1/2 a t squared, and then the other parameter, or the other coordinate for y is just going to be L cosine phi. So now we see that this becomes a function of both phi and t. Okay? So that is, so it's clear here that the relationship between r and the generalized coordinate phi do depend on t. Okay, now let's talk degrees of freedom. Okay, again, if you are just tuning in, the notes are available on Discord. I will not be writing all of this down. If you go to Discord, !Discord to join, and then discussion series notes, you can find these notes there. I will not be writing pretty much any of this next section down. But we can talk about it, right? So we're going to talk degrees of freedom, right? Degrees of freedom are basically the number of coordinates that can independently vary in a small displacement. Now, what does that mean? Well, let's give you some examples, okay? How about the simple pendulum? How many degrees of freedom did we have? Well, our function just ended up being r of phi for just a simple pendulum, right? That was it. Phi controlled the displacement. That was it. Wherever phi was, we could figure it out. Now, what else do we have? How about the double pendulum? Well, the double pendulum, we realized, had 2 degrees of freedom, right? Phi 1 and phi 2. If you knew phi 1 and you knew phi 2, you could roughly figure out where the displacement was, but like I said, there is situations where this does become chaotic, especially once you start including time. Okay? Next, how about a particle free in 3D? So if I'm, let's get one of my golf balls here. So now, we go from the pendulum to double pendulum, but now what if it's just this ball and it's free to move however it wants, right? Then I could go this way. I could go this way. And I could go this way. Right? So three dimensions. There's 3 different degrees of freedom that I can move. What if you have n particles? So, a multitude of particles in a 3D box. Well, in a 3D situation, think about the gas that's in the room that you're in right now. Hopefully it's just oxygen, or air, I should say. But think about all of the degrees of freedom that those particles have to move. It's going to be completely 3-dimensional for every single particle. So your actual system is going to have 3 times the number of particles because there's going to be 3 degrees of freedom per particle. So your entire system, you'd have to consider every single particle. So that's 3n, right, for n particles. And then there's some other examples that you guys might be more familiar with that are not necessarily from this section or from anything like that. It's like your things like, you got your quantum spin, right, fermionic spin, or boson spin, right? Integer spin or half integer spin. Those are degrees of freedom. A fermionic system is going to have 2 degrees, or fermionic particle, I should say, is going to have 2 degrees of freedom. It's going to have spin up and spin down. Spin degrees of freedom, we call them. Okay? And then there's also things like the quark. Quarks have color degrees of freedom. You have red, green, and blue. Those are the 3 colors that a quark can be. They don't mean anything other than that degree of freedom. Okay? But Taylor does make mention of this term, holonomic. It's a system with n degrees of freedom, can be described by n generalized coordinates. That's like one of these, right? You have 1 degree of freedom, 1 generalized coordinate. So n degrees of freedom described by n general coordinates. We call that holonomic, and those are nice, easy systems that we can work with. Non-holonomic systems can be complicated, and we just don't really discuss them too much. But however, for holonomic systems, we have the nice Euler equations that I did introduce earlier on. So let's just make that statement really quickly, and then we'll go ahead and prove it. So we want, and we're going to use all of this and probably some of the next board over as we start working through this little derivation. We just kind of want the generalized statement that for a holonomic system, everything can be described by the equations of motion, just like it was earlier, and that is to say that for holonomic systems, the Euler-Lagrange equations, what am I doing? Wow, okay, there we go. Euler-Lagrange equations are true for any generalized coordinate. And this is, of course, for I, again, 1 up to some n generalized coordinates. Now, n is not necessarily the number of particles, but like I said, we do want this n to be holonomic, so we do want the degrees of freedom to match the generalized coordinates. So let's prove this statement, okay? Let's consider one particle constrained to a surface. What does that mean? Well, this has a screw in it, which makes it difficult. But imagine a ball rolling around on a table. That's the best situation we could think about, right? A ball rolling around on the table. This is a constrained situation, right, on a surface, presuming it can't fall off, right? You just have something moving around on a 2D plane, and you can describe that system by 2 degrees of freedom, right? You have Q1 and Q2. So we have 2 degrees of freedom. So let's do a capital F. For this system, it's Q1 and Q2, okay? We know that the particle will have several forces acting on it, such as the constraining force. Now, what's a constraining force? You might think right off the bat that the constraining force might be gravity, but it's not actually. The constraining force is something that's basically stopping gravity. Gravity would be an external force, right? In this model, I know that it's a little bit trickier than that. Gravity is not a force. In before, gravity is not a force. We're going to model gravity as a force. So, so what's the constraining force? Well, that would be like the normal force, right? The thing that's pushing back on the ball, that's stopping this chalk from falling through the table, right? We always just call it a normal force in intro physics. What is it? Well, now we're just going to generalize it as the constraining force. I'm going to drop all of the vector signs, but you guys know what vectors are and what's not. And then we can have such external forces, right, like gravity. And these external forces, we can write the resultant of those external forces as the negative gradient of the potential energy, right? That's hopefully something you guys have spent some time with, either in classical mechanics or your introductory physics, that the negative gradient of the potential energy is what a force is. And the resultant forces can be summed. Welcome to the channel. Things get a little bit weird. Thank you for the follow, Bryce. I will get to your question in a minute once I'm done with this stuff. And this is not like a university thing. This is literally for you guys as viewers. So yeah, so I'm not constrained. But I do want to make sure that we get this through because this is what you guys have asked for. So now we have the total force, and that's going to be equal to the forces of the constrained, like the normal force or whatnot, plus this other force right here, right, where we have the force of the external forces, gravity. I don't think friction was one, but you can consider other forces, a push, something like that, electromagnetic, whatever's making the force of the object onto the table, and then or pushing it across the table or something along those lines. And then, of course, we're going to be sticking with our normal Lagrange equation of u plus t. I don't know why I wrote it like that instead of t plus u. It should be the same thing. Now, we're going to consider 2 points. Okay, we're going to go this is going to be a good review because this is back to our, kind of the way that we've been deriving this stuff all along, right? We're going to have some path. We're going to go from the origin out to some r1, r2, where we're going to have, some path that goes out here. And the question is, what's the smallest path, right? The least action path. And what we did last time, and we're going to do it again, is we're going to take some outside paths. we're going to write that as r of t, big R of t, which is going to equal our little r of t, which is the path. We're going to assume that this path, the smallest, least action path, the one that we want, Taylor keeps calling it the correct path. Friction is not normal to the surface. We're not going to get into that right now. So what we're going to do is, so this is what Taylor calls the correct path. This is the least amount of action. But this other r is going to be some variation of that, right? We just want a small variation, something that's going to change it. And then we want to find out what this actually is. And if we have chosen the smallest amount of, if we have chosen the smallest path, r of t, by following our prescription here with this, then we should get this entirely to go to 0. Let me be a little bit more mathematical about that in a second. But let's define the action as the integral from t1 to t2 of the Lagrangian, but now of big R, because we want to let the path be more general. Okay? Let's drop the vectors. Okay? So let's keep going with this, and then we'll talk more about. Again, if you wanted to see how we actually derive the least action from using the calculus of variation, you can catch that in the first couple videos. That's all that we're going to be using to do this as well. Okay. So now we have a goal. Before we state the goal, we can denote s sub 0 as the action integral, i.e., that's the least action integral. And what that should be this again, except instead of this big R, we want the little r, right? The least action integral will mean that, and again, we did the calculus of variations, that any slight variation is going to be 0. So mathematically, or let's say the goal first. The goal is to prove that s is a stationary integral when, so s is stationary. Let's write our goal down. S is stationary when big R of t is equal to little r of t, i.e. we got rid of the small variation, and we're just back to our what we call the least action. So we want to make sure that that the variation in s, which is basically saying that the s integral with our big R minus our least action integral, which we're going to say is the little r, is equal to 0. Can we prove that that is true? That's going to be the goal. Can we prove that that's true? Let's get to work. So firstly, let's write down the small variation of the Lagrangian, just so we have a good idea of what that is. That's going to equal the subtraction of our Lagrangian of big R with our subtraction of the little r. And we should also note that the Lagrangian of little r, which is also written as t plus u, is equal to 1/2 mr dot squared minus some potential u of t. Okay, so that's just the Lagrangian, right? We kind of established that off the beginning, that the Lagrangian is just t plus u. So there's what it is written more formally, right? Now, can we rewrite this? Well, let's write this down, right? It's like, can we rewrite the variation on L? And we can. It's going to equal 1 plus m times r, and we're also going to rewrite this in terms of what we had before, where r of t is equal to little r of t plus epsilon of t. Okay? So r dot plus epsilon dot squared minus r dot squared. I have an equals in the notes, but it should be a minus. Let me confirm. Yes. So in the notes there, I have an equals the potential, but it should be a minus. Again, forgive me. I'm shaking off the rust, the cobwebs here. So then we can subtract the potential terms, which are u r plus epsilon t minus u of r and t. Okay? So that's the variation in L. And that's what's we're looking at, and that will be important once we start trying to find the integral itself. Okay. This is what it simplifies to. We're going to use a theorem that is for a scalar field, or a scalar. I'm sorry, a scalar. I don't know what I'm talking about. A scalar. And this is derived in Taylor, but I did not actually do the derivation itself. But it is relevant. Oops. There we go. So for some scalar, this is relevant, right? And we're going to use this for the vectors, or I'm sorry, the potentials up there, and find that it's m r dot dotted with e dot, or epsilon dot, I mean. For the kinetic term, right, we're just going to multiply this out. We'll end up getting, why did I write, what? Hold on. 1 over 2m. Excuse me, guys. 1 over 2m. That makes a lot more sense. Surprised no one said anything about that. You guys normally catch me on my kinetic energy terms. If you guys ever catch mistakes, it's on my kinetic energy terms. So this ends up being, you'll multiply this out, you'll FOIL it out, you'll get r dot squared minus r dot squared, so those two will go away. Then you'll get your middle term. And then really all that's left is this middle term right here, right? Because epsilon is small.
I gave up on your kinetic energy terms.
So epsilon squared is small. Hi, Sarah. Good to see you. So epsilon is small, so if we square it, epsilon squared is even smaller. So we're gonna get rid of that, and we're gonna get rid of it in this term right here. Then we introduce our theorem, and we get e dot the gradient of u, and then we'll have some higher ordered epsilon squared terms, and like we're not gonna worry about those; they're too small. Okay. And then we can write our variation of the action integral. Whoa, my chalk got flipped upside down. And I'd like to take a minute, just sit right there. From T1 to T2 of the variation of the Lagrangian dt. We can then substitute our variation of the Lagrangian in, and what do we get? We get the integral from T1 to T2 of m.
I thought the top part of your screen was cut off, but then I scrolled up and everything was okay.
This is the nice. Who was that? Boring manifestor. So we can then take this Lagrangian and we can simplify it again to the following minus the Lagrangian, or minus the integral from T1 to T2 of epsilon, and we're going to pull an epsilon out, and we get mr double dot plus the gradient of u dt. But we defined r to be the least action path, so this right here is the total force, right? Okay, so let's keep going. We're almost done. If mr double dot is the total force, oh, where are we at? We gotta go back over here. Then what does that term become? You may ask. And I'll tell you. F total is equal to F, remember the constraining force, plus the force from the external objects. And we know that the forces from the external objects are going to equal, the negative force of the external objects equal the gradient of u. So what does that mean? That means once we plug this F in here, we get the total force is equal to the constraining force plus this external force, and then u is the negative external force, or gradient u, excuse me, is the negative external force. So. This becomes the variant of S is equal to negative T1, T2 of this epsilon dot F of constraining force. However, the constraining force is perpendicular to the surface. We talked about that. It's the normal force, right? So if it was like, if you were doing your physics 1, your introductory physics, the normal force pushes up off of an object, right? It pushes up against gravity. Gravity pushes down. That's an external force. The constraining force is the normal force. It's the reason why this doesn't go through the table, but instead lands on my book. The book is applying a normal force in the y direction to counteract the gravity. That means if it's applying it this way, and our epsilon was a variation, remember these are both vectors, epsilon is a variation of the path being on the plane. That means we have one like this, and one like this, and that means they are perpendicular. If you have two forces and they're dotted together perpendicular, remember the dot product, A dot B is equal to AB cosine theta. If theta is 90, cosine theta equals 0, which means that the variation is 0. And we are indeed certain that the variation in S is equal to 0. So then the last remarks on the topic are we can express the integral in terms of the degrees of freedom. And by doing that, so instead of, remember what we started with. What we started with was saying, hey, we're going to take these displacement vectors, we're going to write them as generalized coordinates. We showed that last week. We showed that 4 weeks ago, where the general displacement, or the displacement could be written as general coordinates. And then today we're just saying, so then in the beginning we just said, hey, we could take all of these r's and express them as q's. And then vice versa, we could take all the q's and express them as r's. So what does that mean? That means that we can go back and rewrite our action in terms of q. And if the action can be written in terms of q, and that q is in fact the least action, then that goes back to our original statement saying that we could then write our Lagrange equations, and that this was in fact, ddt, that this was in fact true for each of our generalized coordinates. Which in this case, there's only 2 generalized coordinates, right? That was one of the first things we said when we started the proof, is that there's 2 generalized coordinates, and for this, we proved that if we could write R as generalized coordinates, then everything boiled down to our nice Euler-Lagrange equations. Woo! Hey-o! We did it! Vice versa. Vice versa. Versy? Thanks for explaining normal force. I love the normal force. The normal force is an interesting thing to me because it's so complicated, but yet so
You are not that rusty.
I made a couple mistakes. I did pretty good, I think.